a nossa aula, tá bom? E como é pedido aqui pela universidade, o curso é todo dado em inglês, que vai ajudar vocês a entender melhor as coisas. Então, hoje nós nos concentraremos em terminar o que a gente começou ontem. So, today, we're going to finish what we started off yesterday. It's about still epidemiological measures, the fundamental measures, but I'm going to give you an overview of the statistical distribution and why they explain the so-called events that we are interested in measuring, we're interested in studying, and then making those events measurements of different functions of the same measure creates measures of association at the end of the morning. We're going to get to measures of association. But let me go back to where we started and finished last session yesterday. And let's go over a little bit on the statistical distribution underlying the epidemiological measures. Okay. So yesterday we left off on the odds ratio. And the odds, again, I use always the analogy of poker game or gaming or in odds, is the probability of you winning in a game versus the probability of not winning. So if the probability of winning is 0.5%, meaning I have a half a chance of winning, like when I toss a coin, the coin roll over, come down, and it could be heads or tail, right? So that's the probability win is 50% usually. So it says 0.5 on the top, 0.5 at the bottom. If you divide one by the odds, it's going to give you 0.25. Okay, so that's the odds. We went over this with the same example yesterday with some little money. I'm going to skip because I gave you the example to you, and I'm having a hard time reading it. Give me a second because I need this, unfortunately. I don't know how, but the slide didn't come up. It doesn't grow. The letters are too small. I can't read them. So in the epidemiology, you got the odds, right? It's the probability of something divided by something, and the odds of exposure in a case control. So in the risk, you're interested in the probability of disease divided by the probability of the non-disease. That's the odds, okay? And the probability of exposure in the case control divided by the probability of non-exposure. That's your odds for the case control. We went over this, and the odds can go from 0 to infinity. For example, risk can be 0.01. The odds could be 0.001001, something like that. So we went over this exercise, and I also mentioned to you, so you could remember, I brought it back a little bit, that also in the prevalence, you have the odds, very similar to the risk, but they are two different animals. The risk is the probability of something happen over a specified period of time among those who are at risk for that something to happen over that specified period of time. Whereas the prevalence is just the number of things. It's just the proportion of things with such and such traits or characteristics out of a population. So it's good to measure magnitude of issues, the size of the problem. But here and there, we can still make associations, can still trying to use it as a risk, but it's not a risk and it's not a rate. We remember that. So I can also calculate the prevalence of the proportion of something, proportion of people who smoke on the population general divide by the proportion of people who don't smoke. So if it's 0.50 on the top and 0.95 on the bottom, that's your odds, okay? And then we also learned that we need to get to the odds ratio in a case control. And I tried to show to you yesterday. I'm going to finish it off quickly. We're going to go very quickly on this. You got this material. I'm going to send it to you. You can review it on your own pace, study. And at the end of the course, actually going to send you some exercise so you can do it on your own later on. But just to remind you, there's something called condition probability. And I'm just showing a Venn diagram here to show you that the two areas A and B, or two populations, and there's a crossover between the two populations. The area in between is A and B together, right? I'm A and I'm B, and I'm a little bit of both. So the condition probabilities is usually when you want to say, what's the probability, for instance, of disease among the exposed? You say probability, open parenthesis, D for disease, slash or bar, given E, which is exposure. So instead of A and B, you have D and E for disease and exposure. And that probability, condition probability, is provided by theory of probabilistic methods by the combined probability of A and B combined, which is this little area, shaded area here, divided by the probability of B, which is the thing that I'm saying conditioning on. Okay, so if I have in a case control, I start with disease and I start measuring exposures to risk factors, say tobacco. I have cancer cases and known cases, my control. And then I look backwards and say, did you smoke? How often do you smoke? Have you smoked how many years? And so on and so forth. So I'm trying to go retrospectively to the smoke information on that person, right? That's a case control. We're going to go over this very quickly because we had a lecture yesterday. So once you do that, you end up with a 2x2. I'm going to show later on today. And then you have the disease in a column or in a row, doesn't matter. Upside down, sideways, doesn't matter. So you have the disease and you have the exposure among those. So you want to know what's the probability of D given the exposure to smoking. Okay, so that's going to be the probability of the combined A and B, meaning smoker and disease and smoker, divided by the probability of being smoker. So that's your conditional probability. Example here, you have a table from this paper on biometric, which is breathlessness in age among coal miners. Coal miners, as you know, they work in the mines, taking coal out, and they develop something called pneumoconiosis, which is a disease related to the particulates of carbon coming out of the coal that stall in their lungs, and over time creates a chronic inflammation, which is restrictive pulmonary disease, and that gives you breathlessness over time. So you know that the age of the person is going to be related to that stronger than any other disease. Why? Because the longer you stay in a place, the more chance you have to develop the condition. So your age is going to be a good proxy for how long you've been working in a place. Okay. So anyhow, you see this little table here. You can clearly see the proportion of breathlessness by age group, and it's going up from 1% between those who are 20 to 29. 5% between those who are 30 to 39 years old, and then 12% for those who are 40 to 49. The average across all adults that work in this mine, in this study, is 7%. So if you are at 40 to 49, you have 12% chance of becoming breathlessness, basically out of breath. And then if you divide that by the contrast, which is 20 to 29, you have 12 times higher chance of becoming or being diagnosed with breathlessness. So that's what your numbers are telling you. And here I have an example of a joint probability, which is the probability of being A and B, being breathlessness and having an age of such type. So in this case is the age group 20 to 29. Okay, and being breathlessness. So that's going to give you 48 divided by the total denominator. So that's your probability of, in this table, of being classified as breathless, having no breath. And that's going to give you the 1% I mentioned to you. On the other hand, the probability of a joint probability of A and B, it's going to be the 4,087, as you can see in the table here, is the second row and the third column, okay, with numbers. So it's 4,087 people who are 40 to 49 and have breathlessness that divide by the total. Okay, so they have both conditions. So you can follow this, and then you can then calculate many other possibilities. It's called marginal probability. It's going to be a combination of these numbers. I'm not going to go in detail because I want you to get to the cohort study, and I still need to explain the distribution. But what you see here are discrete distributions, applications of discrete distribution numbers. And I'm going to show you why this through the discrete distribution called hypergeometric distribution that explain that phenomenon, having that cross tabulation table of 3 by 3 or 3 by 2 or 4 by 4 or 4 by 7, in which you fix the margins. The margins are fixed. If I take any number here, it's going to affect the next probability. Okay? Remember, in a binomial, I'm going to show it to you. You take some of the cells out, you need to replace it, you need to bring it back, because the probability is the same across the group. It doesn't affect, whatever is your experiment, doesn't affect the next probability. In a hypergeometric, I'm going to show it to you, it affects the next probability. Therefore, it's important that I brought you this was an example, it's yours, so you can look it over and say, oh, this is how this is calculated. I'm not going to spend much time here because I'm going to go to the jugular, meaning go straight to where you need to be, okay? So I want you to read it, to review. I did a little table. Oh, God, it didn't show good. That was last night. Yeah, I was too tired. That to show the risk-odds ratio in terms of those probability. But you still can read it. If you print it, it would be better than that. I'm sorry for that. But you can see how that plays out, okay? So, and actually, this is a proof by Cornfield, the guy who proved that the exposure odds ratio, the risk odds ratio, all estimate the risk ratio based on probability, which is a very Bayesian view of statistics. But I want to go back to why I wanted this beginning of morning session today to be about 40 minutes about the distribution. Because I want you to understand, and I gave you an example here, I want you to read it carefully, went over some numbers, some ideas about joint probabilities, and more important, the conditional probability, because that's what we use in a case control in a cohort study. What's the problem? In a cohort study, I asked the question, what's the probability of disease among those exposed? So it's probability of D given E, okay? Whereas in case control, I have what's the probability of being exposed given that I'm diseased or not diseased. That's the probability of E given D. And that is a combination of the probability of D and the probability of a joint probability of E and D at the denominator. Remember that condition probability formula? So I just wanted to review this because it's going to matter later on so you understand why the risk odds ratio and exposure odds ratio are the same. So let's go back to the things we're interested in. We're interested in risk ratio, which is going to see at the end of this morning, which is a measure of association, meaning risk in one group, the exposed group divided by the risk, and the unexposed group in a cohort study. So I say, okay, let's take the same study we mentioned yesterday. I have 1,000 old adults, age 65 and older, in Clementino Village here in São Paulo, and I'm following them up for 5 years. And my interest is to see how many develop activity of daily living, ADL, of 10, which is the worst possible scenario, okay? And many of them who have some level of ADL, but not so bad. And I exclude everybody has ADL of 5 or more, because I know that they can progress. I'm not going to wait forever. So I need to have, so I exclude those who don't have ADL greater than 5 or greater. Just keep those 0 to 4. Yesterday I say 0, but it's too extreme. In reality, say 0 to 4 ADL, I keep it in my cohort. So now I know that I have a cohort of people, and my interest is not only in ADL. I'm interested in what physical level of physical activity does to ADL. Does it matter? And I'm interested in 4 types of physical activity: domestic physical activity, transport physical activity, leisure physical activity. What's the other dimension? I forgot. Therefore, occupational. Okay. Well, most of the people don't have much occupational physical activity, but they may still be working. I'm classified old. I went to the line at the airport here when I came to São Paulo, and the guy would not allow me. He said, "I'm 67, sir." Saying, "No, prove me." I showed the passport. So, okay. I'm not saying I look too young, but I don't look too old. Okay. And he didn't believe me. So I can be working. I'm working. I'm here teaching you today. So I'm working. Many older people be working. So occupation may matter. Standing up in front of the podium here, actually, good tip for you. If you want to really spend calories, start straightening up your back, solving the main problem of modern men and modern women, which is your rectification of your neck. Okay, stand up, and to better stand up than work on a stand-up desk. Okay. By the way, you're going to see my name involved in that 25 years ago, because we funded the first stand desk experiment in Texas, in the world. And that's what he proved beyond doubt this thing was working. I was the head of extramural research program for CDC, and we funded those first desks in Texas, and it became the norm. By the way, our team also helped to improve the use and distribution and availability of electric bikes, which is now very common in America and Europe. I don't know how much common is here. Okay, first experiment funded on electric bike, mass scale, combination of private sector and things. So why I'm saying those things, it does all matter. It's epidemiology, it's public health, it's physical activity. Okay, so physical activity in ADL. Think about this cohort. I'm interested in them. So I can do two measures only. What are the two measures I have in a cohort? The risk, I can measure the risk, right? And I can measure the incidence rate. Risk is not a rate, even though people call cumulative incidence rate, whatever. It's not. It's a risk, okay? And then to measure that, I only need, to do a measurement association, I need the measurement of risk in one group and the risk in the other group and divide one by the other. I'm saying this over and over and over, okay? So let's see how that works. By the way, I need to mention to you, there are many classification of cohorts. Just remember, fixed cohort versus dynamic steady state cohort, okay? That's a very fundamental difference. And then you have the so-called nested with occupational types of cohort, okay? So I'm leaving it here to you so you can read it. Stable, dynamic. SD means stable and dynamic. I already explained to you. If I have a large population, a town, a village, I can assume that the people coming in is the same number of people coming out, okay? Unless you are in a very unusual region that has an influx of migrants that is never seen before, and it happens some place in the world, but not here in Brazil, not in 99.9% of the cities in America. So you usually have a large population, stable, dynamic, steady state, meaning the number of people dying, the number of people coming in because they're born or migrate in is steady across the years and constant. So if you have a situation like that, yes, you can extrapolate the measures of incidence rate and risk for the whole population. And I showed to you before, reviewed that lecture, there's explanation for it. So you also can tell that from that cohort, I can also sample people to get a case control, correct? And I'm showing here that, first cohort can be looked at two different ways. One way is this way, in which I have any 1 people exposed and any 0 people unexposed at baseline. They're all disease-free, if I'm interested in disease. They're all ADL less than 10. Ideally, in my case, is less than 4. 4 in 0, 4 to 0. 5 and above, eliminate. They don't include them. We don't include them in the study, and I'm following them up over 5 years, okay? So I have, let's say, 500 of exposed to my interest in physical activity, leisure time physical activity, at least twice a week for 30 minutes. So I define. And I have a long list of classification of types of leisure time physical activity, and I include that long list as part of the definition of the event of my interest, the exposure of my interest. Once I have that, I can classify my cohort into exposed to some level of physical activity, unexposed, and I have any 1 people who are in this group and the N 0 people in the other group. You can calculate the risk odds ratio right there. But let's move on. So now consider a classic case control. And a classic case control, I found a way to get random sample. I'm not going to go back there to the lecture on case control because all folks is longitudinal study. But I can sample from them and I end up with A, B, C, D. Remember? And from here, I can always calculate, a risk odds ratio or an exposure odds ratio. Their case control, I better calculate an exposure odds ratio. So I'm going to show you the exposure odds ratio. I'm still in a risk. That's risk. Come on, where's my exposure odds ratio? Nope, I'm still in risk. Okay, it's my order. I lost my order. It's been a while since I did this lecture. So I can calculate the risk odds ratio. I'm going to skip all of that. Why I'm showing this thing to you? Because there's an exercise. If I had a whole week, Monday in the afternoon, I was going to do with you this exercise. So I entered those exercises here. I want you to do it after you finish this course, trying to answer those questions. And these are here the papers, and I put them in your list. I'm trying to find it. Hold on a second. Okay. What first list is here, handing in quotes, and I have that in your list. And then the next one up is this one here, and these are the questions. So this is not part of the lecture, it is. It's just for you to know that I need you to review this part, like the first part, so that you can try to answer those questions in the exercise. Review the lecture on case control, review the lecture on cohort, which I'm going to complete today on cohort, a full lecture on cohort. And then you answer those questions, and the papers you wanted to read to answer those questions. Those papers have all the ratios that you want to see, okay? It's not relevant now until I finish the measure of association at the end of the morning. So that's the reason I have a few more questions here. Each one addresses a specific type of cohort or specific type of case control design. Okay, so this exercise, it's here. I don't want to put a special exercise and send it to you as part of the lecture so you can follow, because I'm also, before the questions, I do a little explanation. I show some of the calculations again to remind you. So you can review this and then try to answer the questions. Read the paper and answer the question. So this is actually an exercise that the other paper see. I want to tell them what's the source of cases for your case control study. What's your source of this? Because understanding your underlying cohort allow you to answer the question about your case control too. Okay, and I give a little bit of an overview. Don't want you to see that before you do the exercise. Do the exercise, then you take a look into that. That's a little bit half of your answers there. Okay, so let's go back to the real issue I wanted to emphasize when I started showing a little bit of condition probability and a case control coming out of a cohort sample. Okay, and they are the discrete probability distributions. You need that general information so that when you go to measure of association, you begin to understand why I'm doing a statistical test this way, why I'm doing an analysis that way, what type of analysis I need to do for this specific situation that's a little different. I'm going to show you tomorrow to you, intervention trials, they are not perfect. They are not randomized fully. They're pragmatic trials. It's very important to show you because in practice, that's what happened a lot of time. So you need to understand where the discrete probability distributions come from, what they are. And I hope I have facilitated for you. This morning, I did some calculation in Excel, and I play with some numbers. I recalculate. So I have an old lecture here. I modify, put something in Excel. Until about 2014, 15, Excel could not do that, what I'm going to show to you today. But now they can. You don't need fancy statistical software and pay for a fortune. You buy your computer today, Excel comes normal for the past 10 years, right? It's part of your package. So I did a little bit of Excel manipulation to show you how you can get something that's very important when you're dealing with this. And I want to give some examples. So consider a traditional case control study conducted with the underlying cohort that I mentioned to you. Every time you do a case control, you think about what is the underlying cohort study here? Am I sample the true possible cases in a cohort study, the diseased people in a cohort study? Am I sample correctly the true controls and theoretical cohort study? They don't have control, they have unexposed and exposed, but then they have people develop disease and people don't develop disease. That's where I'm going to sample my control from in the cohort. So when you have that, which I did not focus too much, but I want to give you a little bit of the discrete distribution for case control. Why? Because case control is a quick, dirty way to do a cohort study, and they're all connected. Okay? So consider a case control conducted in an underlying cohort in which all cases are incident cases. They are new cases of the disease. You're doing the study in 2023. I don't want anybody who had the disease in 2022 because they're not in my current study period. Therefore, I don't need a study period in a case control, but I need the underlying cohort case period, time period, okay? So I need to understand that. So I want incident cases. Which is the best? Always forget prevalent case control unless you're really forced to do it because you're not doing too different than a cross-sectional study, than a survey. So controls a random sample of the cohort. So that's a very traditional, classic case control. I found a way to randomly sample from the cohort, okay? And they are supposed to be disease-free at midpoint of the follow-up. So it's like if I could sample the midpoint of the follow-up period. I have an underlying cohort, I'm imaginary underlying cohort, and I'm sampling for them. I end up with my A, B, C, Ds. The disease group is A plus B. The non-disease group is C plus D. I think I replaced this. It should be a plus on the top. negative at the bottom. It doesn't matter, actually, for hypergeometric. It's going to give you the same value, I promise you. Okay? So you have your odds, and if you divide the odds of one group by the other group, that's your odds ratio. Okay? Well, we're beginning to get into measure of association. Okay? And I'll give a full lecture on that, but I wanted to have an appreciation for these discrete distributions. So the first distribution of our interest is this baby here called hypergeometric distribution. It has three parameters: capital A, capital N, and mini n. Okay? And the expected value of that variable, the expected value of x, the random variable, or the actual mini x, which is the value that I observe of the random variable x, that is found by multiplying n, in which n is divided by n. Okay, and I'm going to explain the terms here. And that's the variance formula. It's a scary formula, but it's not so bad. So, what is a hypergeometric distribution? We're going to go back to that formula, folks. The formula, oh God, it should be hypergeometric, not Poisson. Sorry, folks. And the formula is not that one. The formula is this one. Sorry. I got, cut and paste and trying to replace it, but I did not replace it right, apparently. So the formula is k choose x, n minus k choose n minus x, and big N choose n. So what I'm talking about, big N is your total population. A is the total items of your interest. Okay, that's your possibility universe of what you're trying to measure, your x, probability x to x. And n is your sample size. So the example I'm giving here, and I did that in Excel for you, is a poker game, and you have a card hand, a hand. What's my hand? And the hand of poker is 5 cards, remember? So I only have 5 possibilities, okay, for the card. Let's say I'm interested in spade. Okay, how many spades I have in a whole deck? So the whole deck is 52 cards, and that's your big N. And okay, let's say your population of the city is your deck of cards. 52 cards, the population of a city of 500 people, a small town, small village. Okay, and then you have your total item of interest. I'm interested in spades. I'm playing poker. I use poker because 80% of the people I know play poker once. Okay, so 13 spades you have in a poker game. 52 cards, 13 of those are spade, espada in Portuguese, right? And then you have your sample size. You say, okay, what is my sample size? I random sample from the population. In this case, my random sample is given by the dealer. You only get 5 cards in poker, so that's my random sample, right? It's a random sample. You shuffle, right? You shuffle and distribute the card. It's a random sample of 5 cards. So that's my experiment. 5 cards. That's my hand. It's called poker hand. So my poker hand is 5 cards. So I can ask the question, what's the probability of having 2 spades? 2 spades, 2 cards, that's spades. 5 cards, that's spades out of 5 cards. 0 card, that's spade. And these are the probability. Okay? And the probability are calculated with this formula here, which should have gone here. Sorry for this. This is the probability. This is the Poisson formula. But the remainder is okay. It's a discrete distribution. It's equivalent to the binomial, but without replacement. Meaning once you take a card out, okay, it affects the next probability. If I take 1 card out of the deck, I took 5 cards, right? That's what my dad was doing in Las Vegas. The 5 cards is out, okay? He's already counting there, 52 cards. There's only that many possibilities for spade with great probability. So he was thinking like that already. It's amazing, the memory of a person. And the more people play, and if you can look at your card for a second, it's even better, his odds. He doesn't need to look at your card, but if he looks, it's even better because he's basically calculating probabilities. So what you have here is that you have a 5-card poker hand. The probability change for the second draw of cards. So the second person who gets, that probability of getting spades already affected by the first one because you remove. Let's say you got by luck 5 spades, right? There's only 13. So now you have a smaller chance of getting the 13 cards. And they're all combinatory analysis. That's why the formula is like that one. It's basically K choose X, that's combinatorial analysis, right? Analysis combinatória in Portuguese, right? That's what you call it. Okay, and n minus k, n minus x. X is your random variable. That's the value you want. Say, how many spades I'm going to get in 5 on the hand of poker that has 5 cards? I think I'm going to get 2. So what's the probability of getting a 2? It's here. Probability is about 0.27. So I have a 27% chance of getting a card, 2 cards at spade in a poker hand, the first poker hand, and so on and so forth. So that's what I'm talking about. So probability of success changes with each draw. It's a discrete distribution. I can only have values within specific, fixed margins, meaning I had 5, a sample is 5, there's only 5 possibilities, 13 possibilities in a total stack. But in my card, I have 5 possibilities only of getting spades. It could be 0 spades, 1 spade, 2, 3, 4, or 5. It cannot be greater or less. So it's a discrete and has this dimension that you see here. So what I did is I went to Excel. If you type in Excel equal, capital letters, hypergeon dot dist, in the parentheses, you put your arguments. Your arguments are, I want to know what are my chance, my odds of getting 0 spades in 5 in a poker hand of 5 cards. Okay, so that's my first argument in Excel. And the second argument is that what is my sample? What is my experiment? What is my sample size? It's 5. You see that? And how many things of that type is there? And that's 13 spades. Okay, and what is my total N, my size of the population I'm talking about? 300 in a city, a little town, 52 cards, that's a maximum. And if I type false, it's going to give you the probability density function, or PMS, probability mass distribution of the hypergeometric. If I say true instead of false, it's going to give you the cumulative distribution, which is a little different. It's going to give you the probability of 0. Let's say I have written here 3, 5, 13, 52 in Excel. And instead of false, I have say true. You have given the probability of being 0, 1, or 2. The summation of this probability, it would have been 0.4 something, 0.3 something, and 0.2 something, 0.3 something. So the combination of those be about 0.8, okay, or 80%. Okay, so that's the cumulative distribution probability. You get that by typing true instead of false. So that's Excel, and you can click in Excel and learn how this is done. So you begin to understand the dynamic of it. I did poker card. You can mimic that and think about sampling from people and end up with a 2x2 table. People have 5 races, race ethnic groups. There are people of all types of race ethnic groups, 13 or 10 or 7. And then you're interested in the cross-tabulation of that with education. And see if education is connected with race. You're dealing with a hypergeometric distribution. And that's what you're doing. You're going to choose N, choose X, say, okay, how many people I'm going to have with this and this? That's a conditional probability. And you can calculate with Excel. You don't need great statistical stuff. And it's very handy. And I can't read this again. Damn it. I'm sorry for it. Put it too small and I couldn't make it bigger. I just pasted yesterday in a hotel and it's not good. Yeah, it's the hypergeometric distribution. You can read a little bit more about it. And you can see in this example here, I think I used it's an old table, 2x2 in a case control, and you have some numbers there. And here's the calculation, the formula I mentioned to show to you before is calculated with those numbers there. You can look at the example. But I want you to have an appreciation that in a 2x2 table, what you have is fixed margins, and you can call that in a case control is fixed margin because you start with a disease, which is your underlying interest is the disease. What caused the disease, right? But you measure exposure. Whereas in a cohort, every little column of the cohort or row is a independent binomial distribution. Here, the whole table is a hypergeometric distribution. See the difference here? So the way the binomial creeps in a cohort study is that the whole table is a binomial, and each column of these exposed people and exposed people is a binomial. And A for the cohort study, I'm going to show to you, is the random variable. Here, I can call X the random variable, but X is everywhere. If I take X, I know that the next one is going to be N1 minus X. So if I remove X, it affects the next cell because the margins are fixed. Okay, so that's the formula again. Very important. I give an example, you can follow through. Then you have the exercise over there. So the hypergeometric distribution is critical to understand why a case control hypergeometric distribution. You know, understand why. Because in a case control, you start with a fixed table like this. Your margins are fixed. N1, N2, M1, M2 is all fixed. They're not the real M1, folks. If you're dealing with disease, instead of white, like race here, see race, and the in-sample, not in-sample, that's a different experiment. But if you have disease and exposure, the M is not the true M. You're interested in disease, but it's not the true M. It's a sample and it's a fake kind of, you know. So what you have is fixed margin, and what explained that is a hypergeometric distribution. And that's why you need to understand it and say, wow, that's why I have a chi-square statistic. Okay? And a chi-square, if I have large numbers, the chi-square is turned into, it's a hypergeometric distribution turned into a normal distribution, a Z. Chi-square, okay? If I take a square root of the chi-square, I end up with Z. The X is actually Z. It's a Z distribution, a standardized normal distribution. So you begin to have an understanding how these things relate. I know it's too short in a course like that to throw all of that, but I want you to at least have it. We say, do not mention all the cohort in intervention trial, but you cannot talk about cohort without giving all that flavor about case control, because case control is supposed to be a sample from underlying cohort, okay? And you are supposed to mimic the cohort and correlate the odds ratio with the risk odds ratio and then with the relative risk. Okay, now we're back to cohort studies. You have the number of new cases, people over time. That's your incidence rate, remember? The incidence density, you sum up everybody's person time, and if it's in a city, you take the size of the population multiplied by 1 year and give it the city size. Okay? I left that just for you to read it. So you have the table like that. That's called density data presentation. As a cohort, I can present an account data presentation or density. What is density? I have the column of disease, okay, but I have the next column, I mean, a row of disease, but the next row is person time. So I have a column of exposed people, unexposed people. I'm calling up over time. So my exposed group here is that people have ADL that are, you know, not ADL. People have physical activity, which is not so good. That's exposure, okay? Whatever is the value we decided. And then the unexposed people have a decent level of physical activity, okay? And then I start tallying over time how many people develop ADL of 10. And that's my disease group. I know I'm interested in anything else. So I only have 2 columns and 1 row, but there's a total. The total, instead of being the number of people, is actually the person time of every person contribute. And that's what we call density data presentation. Remember that, which is different than a column with A, B, C, D, very similar to a case control, but it's actually a cohort, and you have N1 people, okay? So in a density data, you end up with something called the incidence rate. In one group, that's the exposed group, A divided by PT1, and the incidence rate, and the unexposed group. And you have the random variable, it's A or B, could be, but I'm interested in A, the combination of disease and exposure. So that follows a Poisson distribution and has 2 parameters in this distribution. Remember that the hypergeometric had 3 parameters, big A, and N. Here you have 1 parameter. The expected value, which is the mean of the distribution, is lambda, and the, well, in this case, is mu here, but some books call lambda, okay? And the variance of X, of the random variable, is actually follows Poisson distribution with variance mu. So it's mu, 1 parameter only for the whole distribution, okay? It's a discrete distribution, and the formula for it is this baby here. Sometimes written in terms of lambda. I wrote in lambda or mu. You can see both here, so you don't get confused. But some people make a distinction. They say, well, when you're dealing with lambda, you're dealing with a random event A, the occurrence of new cases of disease among the exposed. That's lambda or mu. Others say, no, A is mu. Let's call lambda the rate. You see, I don't want you to get confused. Some books have made that distinction. I wanted to express that so you'll remember that. So some people call this lambda, the Greek lambda here, the rate. You still can model the rate, same way. So it's almost like having two models. One, I model the random variable A, which is a new case of disease among exposed. The other one, I measure the rate. Okay, the rate of the incidence rate of disease among the exposed. That's lambda. What else I know about the Poisson distribution? Different than a discrete distribution. It goes from 0 to whatever is the maximum number of your hand of poker of your experiment, right? It's fixed. Here, I have a different situation. It can go to infinity. It's still discrete over a specific period of time. I'm going to describe a little bit better. You need to understand distribution even better than hypergeometric, because it's going to matter how we're going to analyze this data, how we're going to design your study, and how we're going to analyze. And at the end of the course, we're going to see example in the meta-analysis. We're going to see example in the intervention trials. I'm going to use that to highlight. So the Poisson, the mean variance of the distribution are the same, goes from 0 to infinity, is discrete. Why is it discrete? Because of this. It describes the number of events occurring on a fixed time interval, I call region of opportunity for the event to happen. Okay? So how many new cancer cases will occur in 1 year in Callaway County? Callaway County is a county in Missouri that I had to estimate many times for 115 counties. How many new cases of cancer will occur? Well, that follows a Poisson distribution. That's A on that little table. On that table there, that's A. Remember? Disease in exposed or something. But in this case, for Callaway County, it's not even A. Sorry, I said it wrong. For Callaway County, I didn't specify any exposure, any risk factor. I'm just saying the whole county is A plus B, is the incidence, is the total incidence. Okay? But if I say in Callaway County, among people who are exposed to a chemical plant, okay, that's A. It usually is interesting, called cancer cluster investigation. So if you're interested in that, you follow Poisson distribution. The other possibility is something like I faced it in 1998. Okay, so it came to my attention. This is a true story, and it's interesting for you to know how the Poisson can be applied. That I got a call at 7 o'clock in the office. I was lucky. Usually I don't work that late, but sometimes I do. And then the officer was from Cincinnati, from NIOSH, National Institute of Occupational Safety and Health, which is a branch of the Centers for Disease Control and Prevention in Cincinnati, NIOSH. And this man, I forgot his name now, but he was my co-author after that. We wrote many papers on this. He called me and said, listen, sir, I don't know you, but I have something I need to tell you. You're sitting on a trove of data. I send to your office tons of information about one case in Kansas City that followed by 2 other cases. They're very rare. And I think there might be something there. And I say, what do you mean by very rare? So these are restrictive pulmonary diseases. And I say, well, nothing of it came to my attention, sir, but I will investigate. So next day, I summoned everybody in the office of epidemiology, or state epidemiology. What happened? Oh, they thought it was not important. They didn't bring to your attention. That guy lost his job. Okay, should have brought to my attention, be sitting there for a month. So the case he sent is actually a medical record, because as a federal worker, he has the right to see medical record of patient. And as a state epidemiologist, the law gave only me the right to review medical records of individual people, because I'm interested in public health. So I reviewed the medical record. Luckily for him and me, it didn't take too long, because I work as a pulmonologist, so to speak, for 1 year in Recife, doing, what do you call it? Computerized spirometry. Okay, that was back 40 years ago, the first spirometer that was computerized. So we measured the flux of air, and I could see what he was talking about. It was so unusual what you're seeing. These adult people, age 30 to 50, nobody's supposed to have restrictive disease. Like you have and 2 of them are not smokers. So he was very curious about that. So I investigated the case, and I ended up doing a calculation, a very simple calculation, a Poisson calculation. I didn't have Excel like I did here today, folks. So I calculated what are the odds of having 3 cases of a severe respiratory disease with restriction characteristics, similar to the top ultimate emphysema. You're about to die of emphysema. That's how bad this thing is. And it evolves very quickly. It's called bronchiolitis obliterans. Okay, what are the chances of having something like that? So look at the record, say, find my lambda or my mu. What do I have? So I go to the review. CDC has data 5 years earlier in a nationwide estimation of restricted pulmonary disease. So I found it and say, nationwide, you should expect X number of cases. That's my mu. That's my mean, right? Actually gave me the rate, which is lambda. So with that, I calculate. Back then I had to do by hand, but it's not too difficult with a calculator. Apply the formula, and the chance of that thing happening by chance was 1 in 10,000. So it's very rare, extremely rare, right? So I say, let's open investigation based on that. So that's very important. Legal, later on, 2 years later, they're trying to sue the state. And when they went to the jury, the guy say, a chance of 1 in 10,000, the judge say, Dr. Simões is correct. He needed to open an investigation. He lost about $100 million. But bottom line, making a long story short, the POSO helped you to investigate stuff. We investigated, became one of the biggest cases in America of bronchiolitis obliterans. And we found a new cause of disease that didn't exist before, which is called diacetyl, which is a chemical that used in food to give taste, and more important, to give better tasting to microwave popcorn. This is a factory of popcorn. Later on, we found 17 other workers in a group of 150 people working. And I went back in time, 20 years, we ended up finding 40 and 50. All of these people died within 5 years once they developed the condition. And I found, well, it's an interesting story. That's a whole lecture in epidemiology. There's a lot of other stuff about investigative epidemiology. But if I did not know POSO, I'm not interested, I wouldn't be doing that. But I was interested in the incidence rate, and the incidence rate was so absurdly, interesting, because that gave me a probability that was very rare of that event happening. So it's not just the incidence rate. Think about the probabilistic events around it. So you can also calculate that in Excel. You type capitalized letters in Excel, equal Poisson.dist, and put your argument in Excel. So I wanted to calculate, and here's the example. I wanted to calculate what's the probability of my X, my mu is actually 4. I know that mu is 4. What's the probability of finding 5 cases a mu is 4? Okay, just throw any number here. And I then went about and calculate for everything. Where's the, oh my God. Where's my graph? Oh, here, that's the graph. Okay, so with a mu of 4, the probability of 5, it's about 15%. The probability of 4 is actually, because it's close to the mean, right? It's very high. And probability of 3 is very high. But the probability of finding 10 cases is very small. In that factory there, whatever was the lambda, I can't remember, the probability of finding 3 cases was very small. It's like this end of tail here. Remember, this can go to infinity. It goes to infinity. So if it was 1 in 10,000, that number was like at the very end of that tail. It's a different tail. I can't remember exactly the numbers, so I can replicate that. So there you go. A Poisson distribution is the basic distribution for incidence rate or incidence density. And you need to understand it because you can apply for things like that, questions like that, but also to understand the total distribution. So the Poisson event is an event that occurs constant across time intervals. So you have time intervals. So for cancer, the perfect model for cancer is always a Poisson. It's an exponential distribution. It could be a Weibull distribution, it's a form of exponential distribution. But Poisson does very well. There's something else called negative binomial. When a Poisson assumption cannot be fully accepted, there's some violation of the assumption, especially with regard to the constant events happening. Okay? So sometimes it's nearly constant, but not quite constant. Sometimes there's a variance that's a little bit too high. You need to use a negative binomial. But that's very similar to a Poisson. So probability of event happening does affect the probability of next event. Events are independent. I mean, sorry, that doesn't affect. Does not. That's not. Oh, God. Sorry, does not. I'll correct that before I send it to you. Does not affect. That means they are independent. Needs to check the assumption always. If the assumption don't hold totally, but is nearly there, use a negative binomial. Okay? A negative binomial binomial is a form of a Poisson. It's nearly somewhere in between a binomial and a Poisson. Okay. So another trick, here's an example. I calculate Poissons for different mu's, and you can have these equation apply, and you can simplify. Remember, if you play algebra tricks here, you can figure out how the P4 is 1/4 e to the minus mu P sub 3. Okay. And again, the values go from 0 to infinity, and that's the general formula for the Poisson. So consider a Poisson distribution with mu3, the example I gave you. The probability of something happening, say 2 or more events with this type of Poisson mu, that's what you got. It's an 80% chance. If you got a 20, and I did some calculation so you can have an appreciation. So now let's go back to another way of looking to the cohort study. It's called count data table, or the risk. I'm interested in the risk. It's no longer talking about a table that has percentile in one of the rows. I have actually a total of N1 people, N2 people, M1, M2, whatever you want to call it. Okay. And my final interest is the risk, and ultimately the risk ratio or the relative risk. They are the same thing. So end up with things like that. Okay. And the distribution of A is distributed as a binomial. What is the probability of new case of disease happening among the people who are exposed to something? Okay, that's A. And that follows a binomial distribution with 2 parameters, the total N, your sample, okay, and your proportions in the general population. Your big P, they estimate to the sample as small p. Okay? So you always remember the variance of the Bernoulli, which is the base of the binomial, is P that multiplies 1 minus P. If you throw the N, then becomes P 1 minus multiplying 1 minus P, or PQ, some people call 1 minus PQ, and divide by N. That's your variance. Okay, and then you take the square root. But here I'm looking at the variance of A, not of the whole ratio. Just the variance of A is NPQ. The variance of the ratio of the proportion is NPQ over N. It's PQ over N actually. And the standard deviation is square root of that. I didn't give all the formula, but you see that later on when you go over the cohort. And I showed the formula. So now you don't need to remember why this formula. Now you know where's it coming from. Okay. So binomial is also a discrete distribution, 2 potential outcomes of interest only. Yay or nay, yes or no, disease or not disease, and so on. That's your interest. The probability of success is the same across all trials. Every time I sample, I get the same P. So you do a random sample of telephone numbers in the city of São Paulo, phone list, a random sample of that. Everybody has 1 chance in N of being reached. N is the total list, the framework. I have 10 million telephone numbers. So I have N is 10 million. That's 0 N. Okay. So I take 1 person at random, that's 1 over N. And that's the probability that's fixed across. So a sample is always a form of binomial. But here we're talking about probability of yes or no, probability of being disease or not disease, special. Okay. Number of trials fixed, each trial is independent. For example, diabetes, the proportion of people with diabetes in the population, it follows a binomial distribution. Okay, if I have a population of 100 people and I know the P in the general population in the city of Columbia where I live is 10%, the prevalence of diabetes. So that's my big P, the population P. So I know that my P now for my binomial is going to be 10%, 0.10. And I have a sample of 100 people, so I have N of 100, and then that, so what do? NPQ, right? I sample 100, multiply by 0.10, that's NP, right? And then I multiply by Q at 1 minus P, that's 0.9. Whatever number's got that. That's your variance for this A, the number of people who have diabetes. The variance for the proportion is that divided by N, square root of that standard deviation is PQ over N. I'm not going to bother with that. Take a look into that. So in a random sample of 10 adults, what's the chance that 1 among them is diabetic? What's the chance if P in the population is 10%? If I sample 10 people randomly, what's the chance of getting 1 diabetic? 10%, right? So the probability follows Boston. So I did Excel again, it can help you. You can say equal binom dot dist, and you can give the argument. The argument is going to be, what's the probability of getting a 0? The example here is 0. If the P in the general population is 10%, I'm sorry, it's 10%, 0.1, and the sample is 10 people. I sample 10 people randomly. I know that I should expect 10% diabetes in that population. So if I sample randomly 10 people, how many should have 0? I calculated. The probability is 35%. It's here. I actually calculate the probability of, I did not calculate probability 0. I calculate probability 1, 2, 3, 4, and 5. Sorry. I should have calculated the probability of 0 also. Okay, so the distribution would have a left tail here too. So, bottom line is you can do that with Excel, come up with this crazy formula here, which also has a little bit of a trick, and you can play algebra with that. The log of that is going to turn everything into a linear summation. You could take it off. Not going to spend much time. I just wanted to give you the distribution. We already went out, right? Yeah, I need to stop. So let's go quickly on the binomial a little bit more. This is for you. It's called Bernoulli. It's the basis of the binomial. Pay attention to that. Is 0-1 type of failure. Okay, I can only have 0 or 1s. It's very used in industrial settings, but not so much in medicine. I use the binomial. I have the binomial. It's very similar to the binomial because it is the base of the binomial. And then you have the binomial distribution formula, which I already gave it to you. And there are other ways to calculate it. PQ over N, I mentioned that before to you. The variance, PQ over NP, multiplies 1 minus P over N. And the parameter expected value of P, I kind of derive from the expectation, and P over N, we end up with P. So expected value, what should be P is always P. Okay? Last sample approximation, because you're going to need that later on when we go through cohort. When N, the N of your sample becomes too large, you approximate the normal distribution, especially after 30. If you have 100, you can use either. You can use formulas for confidence interval and test the probability, both normal distribution or binomial. Okay? The other important thing before we finish this thing is to say that the binomial and the Poisson are cousins. And that's why they are part of the cohort study. And you can see the derivation here. I derived it for you. Many other people have done before. If your N becomes too large, goes to infinity. First off, it becomes a normal distribution. You can apply standardized normal, not just any normal, standardized normal distribution. But if it becomes really large, a binomial turns into a Poisson. How? N goes to infinity, P turns towards 0. If the N, the population is too large, whatever P you had before tends to 0, right? Becomes too small. The number of events becomes too small relative to the size of the population. So you N, it's a limit. It's the limit of P as N goes to infinity. So that limit is going to give you that formula. I derive it for you, and you can see how the Poisson, the binomial turns to Poisson. And I can do it vice versa. Okay. So there's something else I want you to pay attention, that the risk can be estimated by the incidence rate because of that. If binomial can be a Poisson and Poisson can be binomial, yeah, they are related. And there's a tricky, simple way in calculus, and I give it to you. I can't read this. Damn it. Oops. Okay? I don't want to do it. Don't worry about it. Just read it. For those who remember calculus, it's just a simple integral. Okay? But the main thing is, in practice, you can use this formula here. Risk equals 1 minus exponentiated of E to the parameter multiplied by T, by the time I'm observing, the number of times I'm observing. And the parameter here is a Poisson parameter. Okay? So you end up with this. This is an example here you can follow. Very important. And if it's across, it's not just one value, across a summation of value across people's different age groups, then you can sum up each one individually and come up with one estimation of risk for the whole group. Okay? This is the example. This is the formula. I derived to you. And the most important thing for you to remember is that all of those things, just to help you understand when you go to a 2x2 table and you look at chi-squares, when you look at probability distribution, you look at how we're doing analysis later on. When you get tomorrow the letter of intervention, let's say, well, we need to use a account data regression, a Poisson or binomial distribution, or a negative binomial. Oh, we need to use logistic regression. You understand because of these, and it'll be easy for me to explain that because I gave you this. The other interesting fact I wanted to give it to you in the next 5 minutes is that prevalence and incidence are extremely related. And this is the way I want you to study. It's very simple. If I could simplify, if a disease lasts for too long, like diabetes, right? Lasts for too long. You're diabetic. If you're good, you can actually get rid of diabetes in 1 year. But if you're really morbid obese, it'll take 5 years doing everything right. You can't get rid of diabetes if it's in the beginning. You're not totally destroy your pancreas, whatever. So, but it's usually a disease for average person with the will and the power of the average person. You take forever, that means they'll never be cured. They will live with diabetes forever. Until about 10 years ago, medicine say, no, you don't have cure for diabetes. Yes, there is cure. It's lifestyle medicine. It's lifestyle change. If you eat right and you exercise every day and you don't touch anything that's overcharged with insulin production, you get rid of diabetes if it's in the beginning. So a lung disease like diabetes, the duration, the D here is duration. That little bar on the top means duration of the disease. And the E is the incidence. So the prevalence on average, with give and take minor error for large population, relates to the incidence in this equation. The real equation is the one on the top. N1 minus PI, NPT, that's percent time, sub R. There's an R, there's a rate there. You can see the term here, termination rate, population size, incidence rate, and prevalence of disease. You can follow that. So just remember, the prevalence is more or less the incidence, the number of new cases. Like I have a bucket, okay? The bucket is full of water, and that water is cases. There's a pipe bringing water in. That's new cases feeding in. There's a pipe removing the water, okay? So that prevalence is the size of the case. The water coming in is the new case. The water already inside is the prevalent case, new and existing cases. So P is equal to I, the new case coming in, and duration, how long it takes that process to take. So the accumulation water, let's say I had a level, then it comes to a level, start draining. But until you drain, that's the prevalence, maximum prevalence you reach. So that's what you got on the prevalence estimation. So if a disease like diabetes is long duration, you always have a huge prevalence in a small instance. On the other hand, if a disease, one example, lung cancer, okay, small cell lung cancer. What happened to small cell lung cancer? Anybody? Can a group do a chat and somebody tell me what they're saying? You die in the first year, usually. Very rarely you go beyond 13 months of life once you're diagnosed. That's the reality, unfortunately. So in that case, your incidence and prevalence are going to be too different. They'll be about the same. But in diabetes, hey, your prevalence is going to be huge relative to the incidence because the disease doesn't kill you immediately. So you accumulate, cases accumulate. If I measure the prevalence, how many people have diabetes? I always have a large number of cases, 10%. But the incidence is not 10%. This might be like 1 in 1,000, 1 in 10,000. Okay? Whereas lung cancer, small cell, old cell, lung cancer, yes, the incidence and the prevalence will be about the same. Okay, that's the relationship I wanted to show to you. Take a break of 15 minutes. We're going to go to real cohort study now. Having seen a lot already about cohorts, to the measure of disease occurrence, to the statistics behind it. And again, this course is to be given in 5 days, morning and afternoon, with exercise. Okay, I'm simplifying a lot of stuff, but I gave you the material of a full course. You will receive, how many slides I did? Maybe 17 or 16. I'll give them all to you. Okay, so 15 minutes break. We go back to cohort study. Any questions on the group there? There are questions? Alessandra, you following up? The group didn't. Yeah, yesterday was more practical stuff. Yeah, maybe later there'll be more. Oh, look, the lecture was not showing. Was it?
Yeah.
It was?
It was showing.
Okay.
Yeah. Just pause the microphone. Yeah, that's camera. Start sharing. About that one.
Tá aparecendo, por quê?
Olá, Michel. A gente está sem possibilidade aqui de compartilhamento. Tá.
Prontinho.
Pronto, obrigado. Now, you're sharing. O vídeo está ok? O compartilhamento está ok?
Perfeito.
Perfeito, ótimo. Here we are.
So we're back. Hope everybody got a good break. We're going to focus now on the cohort study. I put a little guy here for you. I can work all night. Can I be your postdoc? So the little mice here is the postdoc. I don't say you look like them. I'm just saying that that's what they do to postdocs. Make us work hard like a mice. So we're going to talk about the cohort study. We gave you the basic statistical foundation for two measures of the cohort study, the incidence rate and the risk. And we've been talking about those two for 2 days now. Now we're going to talk about the study design. We've seen the study design for cross-sectional studies. We've seen the study design for case control studies. And now we've seen the fundamental study in observational design, which is the cohort study. So all the other two, what they can do is to help us get a better understanding of what's going on in terms of relationships between variables. But they're very hard, especially cross-section. You cannot make a case for causality. On a case control, you do, because what you're trying to do with a case control is a cheap, fast, and smart way to try to do a cohort without actually doing the cohort. And if done right, like an instant case control study, the underlying population is very much well understood. You know you're sampling without bias. And more importantly, let's say in a nested case control, you know that is a true cohort. Okay, you're already in the cohort, you're already exposed in an exposed group. So that you have a perfect design there too. But that's not normally the way. The best way to observational design is the cohort study. And tomorrow, we're going to look into intervention trials, which include the randomized clinical trials, the randomized intervention trials, pragmatic trials, natural experiments. I'm going to focus on those four to give you a kind of a flavor in what we need to do. But here we have a cohort. It's designed to compare the rates of amount between exposed and unexposed. In a cohort, the exposure occurs naturally among the individual that's being studied, but that's a huge difference between experiment and observational design. Both are longitudinal, both are trying to understand what causes what, but in an experiment, you control the exposure. Here, you don't control anything. You don't go tell people to smoke. You observe them smoking, okay? They are smokers. They took up smoking and they just follow up. So subjects are categorized on the basis of their exposure to one or more risk factors. You're not restricted only to one risk factor. You can establish a cohort. For instance, when you do develop a cohort study to study aging, like Dr. Luiz did here 3 times, you get money to build a cohort. In a cohort, there are many exposures they are measuring. At the same time, there are many outcomes they are also measuring. So again, the ADL, activity of daily living, is one of the interests. That's the main outcome of interest. But there are many exposures: physical activity, occupational settings, diet, behavior stimulants, and barriers, whatever. So there are so many things you can measure. So you can have more than one exposure, and each level will have exposed and unexposed. Okay, so you select the population, categorize each person, whether he or she was exposed to one or more of the risk factors of interest. Participants are followed up over time to determine if a disease or condition develops. Okay, so that's your cohort study. So here we have a little bit of more detailed. Your risk factors measured in pre-selected cohort to identify exposed and unexposed. Cohort is followed up. The outcome of interest is measured over time. You tally every time the event occurs. You have to have a system, a registry type. Okay. At the end of the study period, results are compared between exposed and unexposed to test a priori hypothesis. You should not be creating hypotheses as we go along. You should have a priori hypothesis, identify your exposures ahead of time, like I said, and pre-select the cohort to identify exposed and unexposed. You don't go about after third year of your cohort of aging people and say, hey, I'm going to start measuring other things and see how it goes. Not a good idea. Okay, we're going to get into that later. So the perspective of the cohort different than the case control. The case control, you started this drawing here. You start with cases and no cases. Here you start exposed and unexposed, and you look prospectively, always prospectively. Not the implementation, but the nature of the study's perspective. You have a point that you begin and a point that you end. You're following people over time. So cohort is designed to compare incidence rate. You already mentioned that. The exposure occurs naturally. And you end up, when you have your cohort, with something like that. When you write your paper on the cohort, you better write your method section a little bit like that in the beginning, the very beginning, to describe a population. Well, we look into a population of so-and-so place with X number of people. And we create an eligibility criteria. For instance, if I'm doing a study on ADL, and I want to see if people develop ADL of score of 10, which is very bad over time, I made ineligible to my study anybody had ADL of 5 or more. Because they're very close, and remember, what we want is to measure incidence rate in exposed, incidence rate in unexposed, risk in exposed, risk in unexposed. Well, to do that, I need the people who are exposed and unexposed to be very different. I need to create contrast. We call this mathematical contrast. So you want to make sure that you don't have those people in the middle, because what they do is to dilute the measure of association. We're going to look at the measure of association later on. On the other hand, sometimes there's no way of avoiding, because you end up with so few people that you don't have enough power, and you need to allow some people to creep in the study. Okay, so these are the decisions you need to make a priori before you set up your study. Should I include, out of my 1,000 people that I'm going to follow up over 5 years, to start aging in physical activity, all kinds of physical activity, especially my aging outcome of interest, my endpoint is ADL. And ADL of 10 is the worst. Everybody who don't make ADL of 10, they're better off. I can create 3 levels of ADL, actually. ADL 10, between 5 and 10, below 5. Okay? So these are my outcomes of interest. So to do so, the eligibility allows to get people in that allow this contrast to be better. Okay? But sometimes you need to allow people who have ADL in between, like I said, the example of 3 levels of ADL, so that you have enough people in your sample. But usually you want to exclude them. That's the eligibility criteria. You write that in the method. And then you end up with exposed and unexposed. And unlucky to you, some people drop from the study. They disappear. They say, I don't longer want to be in the study, some of them say. Some others just disappear, you cannot find them. So they are the non-participation group. That is selection bias. Because your aim is to select exposed and unexposed. And if you select 500 unexposed, 500 exposed people, and then you lost 100 only in the exposed group, you don't know if this 100, all the distribution of exposure is identical to the others, or something else there's going on. That's maybe for the other variables. So you want to make sure that you don't lose people halfway through. That's lost to follow up as a selection bias. So once you have participant, non-participant, exposed and exposed, then you tally in 5 years, you tally how many develop bad ADL, bad outcome, how many stay in a good ADL or reasonable ADL. That's good outcome. This is a study done by a colleague of mine at St. Louis University and BJC, Barnes Jewish Christian Hospital in St. Louis. cabbage surgery performed in at BJC Hospital during 1999 among obese and obese people. The hypothesis to be tested here is that obese people have more infection post-surgical because of the subcutaneous amount of fat, okay? And also fat under the omentum. Talking about abdominal surgery, general surgery usually ends up being the abdomen, most of your organs are. Otherwise, it's brain surgery or orthopedics, right? Your legs, your members. So basic surgery is, 80% stomach, liver, intestine, pancreas, spleen, bladder, your gallbladder and things of that nature. So you open the abdomen. So if you're obese or overweight, that's where most of your fat's going to be located. If you're a man, if you're a woman, maybe not. You have a lot in your hips if you're a woman. That's a hormone distribution. But here we're talking about adult in general, and many women do have a called android, development of obesity more on the abdomen than things. So bottom line is to say, Terry Leet, that's my friend, he died very early in life. And he said, no, I think I have a hunch. Look at these numbers here in the hospital that maybe obesity is related to it. So he developed a cohort, and we have people going to surgery who are obese and people who are not obese. These are my cohort. And this is a short follow-up period because you enter the cohort when you select to go to surgery. The day you decide to go to surgery, the surgeon assign you a date and a time to have your surgery, you are in a cohort study. And then at that point, a lot of physical exam, a lot of clinical exam, we select the obese and obese folks to follow them up. Okay, well, in St. Louis at that point, obesity, like morbid obesity, was about 15%. Very, very high. Obese and obesity altogether. And overweight was about 20-30%. So you end up with about 35% of the population being the obese group and the other not. That's 1999. So you go over, get to surgery, and you follow them up. I think it was like 2 weeks post-surgery. So it's a short follow-up period. So he was able to look into a cohort like that. Deep chest infection, SSI's infection, surgical infection. No deep chest infection or deep chest infection. Actually, this is not, I was wrong. Actually, it was thoracic surgery because it's chest. So I forgot. But obesity gets everywhere, especially in the abdomen. So you probably open the sternum. So people have a lot of deposit here too. So you end up with a 2x2 table like that. That's a true number there, folks. Okay. Can you come up with an odds here? I didn't put numbers yet. So you have, let's calculate the risk here. If it happens to be a case control, you calculate the odds, but you could calculate the risk-odds ratio here. But let's calculate the incidence rate of deep chest infection among obese people. What's going to be that? Alessandra, pay attention if the people are saying something. For the few people here, any guess here? What's your denominator for?
No questions for a while.
No question. Okay, the obese people, I have 500 obese people, right? That's my denominator. That's the N1. It's a short follow-up. I'm going to use the risk. Because person time with a few weeks or days, we could. It's calculable, and he did calculate too. So I have 500 people in the obese group, the exposed, and then I have 1,500 people in the unexposed. 10 people in the exposed group develop infection. And 15 people in the unexposed group develop infection. So 10 divided by 500, how much is that? 2.5%, right? It's about 2.5%. Okay, so the other group is 15 by 1,400. I don't know. So it would be like a 1%. So you have a risk ratio of about 2 to 1, 2.5 to 1. You see that? So the risk, then here you can say that people who are obese going through surgery, thoracic surgery, they are 2.5 times more likely to develop infection than the other group. You're more likely. There's a likelihood here. There's a real probability, likelihood on a ratio. So population at risk, remember that? People have to be at risk at the beginning of the cohort, exposed and unexposed. Where, So obese and obese people, do you have any reason to believe that this classification violates this principle of not being at risk for developing infection? No, they had no surgery. My outcome is infection post-thoracic surgery. And by the way, SSI is not just an infection. I should have clarified that. That's surgical infection, okay? It's infection on the surgical site. Whatever you cut it, either subcutaneous, on the skin, on the bone, whatever. If it's a thoracic surgery, let's say at the heart, it was open surgery probably to the sternum. So there is a chondroid area here, not real bone, but it's kind of a bony area. But you could have cut some of the ribs. At any rate, so you got it. They're all at risk for developing infection. It's a perfect cohort. I should have thought about that. He did. A prospective cohort. So the difference between a prospective and a retrospective. Usually cohorts are prospective. You start at point zero, you follow people over time. What they call retrospective, how you collect the data, but you still have perspective. You still have from 0 to time X. You with me? It's just how you collect the data. So in a retrospective cohort, you go back to retract the data, but the data already exists. You're not creating data. It's not like a case control, I'm doing an interview or something. The data is somewhere else. We're just gonna, usually you go after records that have that information. So for Terry Lead and his obese stuff, he could have developed a cohort, assigned people in the study groups already to get his cohort going, and then went back. He assigned people. Let's say he assigned, how many people he assigned here? 2,000 people who are going to go surgery. He assigned them to the cohort. They're my cohort study. And he followed them up at some point to find the infection. But not all of them, he had information in the obese. He got the information later. He went back to the records, backwards, I mean, going backwards in time, going back to the day that people have established record and at the hospital, and say, that person's obese by X. Let's say I stop my follow-up here, okay? So it's just the manner you to collect the data. Look back at exposure, okay? The criteria for defining exposed cohort should represent a homogeneous group of individuals with common exposure with a defined population. Everybody knows the story of the cohorts, correct? You know how cohorts are created, all of you, I hope. Quickly, Roman, have you heard about it? Cohort is a Latin word to define people who share commonality. And it was created by the generals, the Roman generals. They're excellent. So they create cohort of fighters in their lines, because the people fight in lines. So the first cohort were the weakest, the shortest, the skinniest, and the least trained guys. The second cohort is better trained, stronger. The next one is stronger. The last one is the elite. These guys never die. They'll kill anybody around them. For every one of them to be dead, they will have killed 15 of the others. So that's the cohort. People share something commonality. That's how they won war. I don't know how the people in the front line accept that, but that's how they did it. So cohort is to identify people have common. The people in the last one first that trained the same number of hours, they're winners. They've been in different wars. They are very experienced, and they will kill everybody around them, even their own people if they stay in behind. At any rate, so that the cohorts share some commonality, should have a relative high frequency of exposure that can be measured. If you select cohort that you have difficulty measuring exposure, you're in trouble. Okay, I do have a cohort like that. Unfortunately, I had to, because sometimes there's no way of evading the issue of difficulty of measuring. I'm interested in heavy metals. So to measure heavy metals is not easy in the body, right? You need to have a special type of blood collection. Okay, it cannot just be serum. It has to be a total blood. Because if it's serum is easy, there are many serum sitting around collected. I could create cohort out of that. But anyhow, just to give an example that usually trying to find something easy to measure because it's going to affect how you create your cohort. Once you define them, they are in your study. And if you start losing information on exposure, you have something else, not selection bias, you have misclassification of exposure, which is information bias with this, affect creeps in the study the same way as selection bias. Should have minimal loss to follow up. Remember I mentioned the participants? You don't want to lose people because you don't know. Unless you lose people, you know everything about them, and you follow them up later to find out if they die or not, if they develop the outcome of interest or not. Hey, but that's the whole purpose of the cohort. If I lost them, I lost them. I don't know. What if everybody who I lost, who are in an unexposed group, actually end up with the condition I'm interested in? You would have been a completely different relative risk. So I should not, and I'll do everything in my power not to lose people in my cohort. Famous cohorts with Framingham study, Tecumseh, the Iowa Tri-County studies, all the special events like war veterans, created many, many cohorts of war veterans, famine survivors. The last one was the cohort in Chernobyl. And then the biggest cohort of atomic, it was those in Nagasaki. They've been followed up for 75 years. Lifestyle, Seventh-day Adventist, Mormon. These are all studies. If you type those names, you're going to find a cohort study about the special groups. You can do cohorts. Actually, they are done in the past. For instance, one of the first cohort studies ever done was suspicion of testicle cancer in chimney sweeps workers, the people who clean the chimneys, on the roof, okay? They go there and clean it in the turn of last century, and they all develop, many of them develop testicular cancer. And the reason for that is that the particles of their condition work stay in their clothing. Once they're taking the clothes off, they always scratch their balls, so to speak. Sorry for being so graphic, okay? And by scratching their ball, they brought the chemical into their balls. They didn't take shower, evidently, because they did take showers, you clean it up. So they take the clothes, scratch the ball, contaminate, and they develop cancer. Chimney sweep and testicular cancer. Steelmakers, physicians, nurses, DES, that's estrogen medication, pregnancy-related nausea. So many type of cohorts are created. Type those key names, you're going to find them. Criteria for defining the unexposed group. That's a very interesting stuff. It should represent a homogeneous group of individuals, the same population. It cannot be a different population. They need to be the same population. I cannot do exposed group coming from one city and an exposed group coming from another city. There's a chance something is going to creep in that I don't know. Okay, people share. I need to have them sharing something. The unexposed need to be unexposed for sure. That's the main sharing. They share no exposure. For whatever I'm interested. So I'm interested in physical activity, okay? Or in this case, physical inactivity. People do minimum exercise. They're all unexposed. But I also want them to come from the same community. So the underlying population has to be the same. Lots of issues, including confounding, not just selection or bias, is the confounding issue. And there are unknowns everywhere. And so you're trying to make them as homogeneous as you can. And again, minimal loss to follow-up of the unexposed group. Unexposed cells from the same population is exposed. That's fundamental. Also, the other way is to make sure they are all exposed and exposed similar to the general population. They don't even need to be perfectly within themselves, but they should represent the total population very well. Source, where do I go to get cohorts? I mentioned to you, pre-existing record is very good to create cohort. Birth certificates, medical records. Terry Lee went to medical records and look, and this is a very large set system of hospitals in St. Louis. BJC system, they're back about 6 big hospitals in the metropolitan St. Louis. So he looked at he found 2,000 people who are going to go thoracic surgery already, scheduled. So he include them all in the cohort, invite them, you need to select them randomly and then invite them. Or in this case, he actually select every one of them. He lost a few, he didn't want to participate, but most of them wanted to participate. So he went to medical records to find them. Measurement from study subject, physical measurements, biomarkers. In my case, I'm looking for biomarkers in São Paulo, in Salvador, and 5 other cities. There's a big cohort with USP, University of São Paulo. Okay? So I'm looking for biomarkers, but it could be anything. Measurement within a relevant environment, work area, proximity to environmental hardness. If you're doing that, you have a way to measure the environment to be careful. Measuring the exposed and unexposed is a key element in a cohort. Okay, yes, it's true for the case control, but the case control you're always going to find retrospectively based on record or in an interview. So case control is even more prone to bias because there's an interview most often, but at least try to validate the question the best you can do. Here, you can do better. You have records. Or if you sample for environment, proximity to the environmental hardness is critical. Let's say I'm trying to create a cohort to study environmental contaminants of a community, and I did that study, okay, around Kansas City. And I present the findings to the community later on, and I missed Erin Berkovich by a few minutes. I'm not kidding. And she came and said horrible things about me, okay, because I destroyed her new case. She was going to make money on that, but she didn't. Truth is, if you do environmental hazard contaminant, how do you select a cohort? So my criteria are very simple. Actually, the people like Erin Brockovich and the others who are not technical, are not scientific, and they had some good cases. They actually are right, but they based on a hunch and they based on conspiracy theories always. So the industry or the people who own the factory are always wrong. That's their mentality. Mine is science tell me if they're wrong or right. So when I say proximity to environmental hazards, if anybody here out there is going to do cohort environmental, think about this. Can a factory contaminate water, okay, with chemical, like PVC, okay? Can they contaminate water with PVC? In a community that has a river going through, okay? Or that which the water tank of that community that they drink from that tank or that, water treatment system is upwards where the factory is, and the factory don't contaminate the river downward. Can the downward river contaminate the water treatment plant that's upward? You know how a river goes, right? Have you ever seen a river going from sea to the mountain? No. And the reason for that is, it should be lost, but it's just, that's how the river flows, gravity. Okay? It may stagnate a little bit to be always being. So if you downstream in a river, yes, the stream of the river got to you. But if you upstream, there's no way a factory contamination can get there. That's called proximity. Very simple rule, okay? But the proximity goes beyond just the environment. When you do environmental contaminants, think about also, do the people live here for how long? People who just moved in, they could not have been contaminated. Cancers usually take somewhere, if it's not childhood cancer, it takes on average 15 to 40 years to develop cancer, for most cancer. Okay, therefore, if you just move in, you should not be part of my study. Your house is not included. See what I'm talking about? So when I say proximity to hazards, it's a bigger than just geographical, physical proximity. But you need to establish some logic for the contaminant to get to people. On this community, many people did not live there before. I removed them from the analysis. Also, they say contamination of the water. It can't happen. It's downstream. The water treatment plant is upstream 2 kilometers. There's no way that water is contaminated. It's impossible. They can do geological, whatever you want to do. It's not going to happen. And then they say, I come to the air. Well, I studied the plumes, called plumes of the air, atmospheric thing. In Kansas City, they have a meteorological atmospheric thing. And they show 90% of the time, the plumes of the air, whatever goes in the air, come from west to east, north to south. And sometimes do a reverse for a few minutes, but that's about 10%. So 90% of the time is that way. Well, the factory was actually on the east of the city, not on the north of the city. The river came through here. So the chance of a lot of these people being contaminated was like ridiculous. Didn't exist, but still do a study. Once to do the elimination, only left a few households, and then, hey, the incidence of cancer there is like lower than the state. Okay, so that's what I'm talking about, folks. Create cohort that makes sense. Source for identifying and assessing exposure, interview, study subject, personal phone. Also, very common to use surrogates of the study subject. When do you do that? When you have problem interviewing the person, because the person is home sick or is in bed, permanently in bed, so you need to use proxy. But you need to know what can be measured to proxy. Proxies are not a person who responds on behalf of somebody. The other situation is parents. For children, for ethical reasons, And parents know a lot about the child's life, more than the child himself. So it's better to use proxies with children than the child himself. Okay, we're back to that study. So the goal of the cohorts is to trace all cohort members independent of exposure and with equal intensity to determine the disease status of each study subject. That is also an important aspect of it. If you do not put the same intensity in measuring everything about exposed that you put in the unexposed group and vice versa, you're going to bias the study. So whatever metric, whatever intensity, whatever frequency of measurement you do in exposed, you do in unexposed. And you try to use the same people. If it's a collection that needs a person to collect, use the same person to collect both data. We already done that. I'll skip a little bit. That's also follow-up information, which is a little, well, this is different. This is how you confirm the disease status. Well, you could observe them and ask a proxy, see if they disappear. But usually in America, you go to vital record. If your ultimate endpoint is death, it's easy. That certificate, you have 100% people there. There's no exception. Here it's complicated. Here in São Paulo, likely 100%. But if you are about 15 years ago, you did a study here in Ceará, Piauí, Pernambuco, my state, and Paraíba. And I think they're about 10% loss of the death. People die and they bury them, but there's no record of that death. Okay? So, so maybe it depends where you are and how you get it. But these are important aspects, so you need to confirm the outcome. For ADL on the cohort that imaginary cohort that I created, you are the one that have to guarantee you know how to measure that. And that measure does not change over time. And it's not different. The way you measure an exposed is the same way you measure an unexposed. And the ADL is usually measured through a questionnaire and create an indicator. Okay? So it should be easy to keep consistency and standardization of process. Source of follow-up information. Sometimes you need more than just the outcome of your interest, but follow-up, you need to get the information about where the person is or something, confounders and everything. So there are many ways you can trace people and see where they are. Okay, professional association is a good way in America. We use a lot. Cohort studies, basic methodological issue. You need to have sufficient variation. I mentioned to you that I need to have contrasts. So the ideal cohort for studying ADL is one that you were looking for ADL of 10. That's your maximum. That's the worst case scenario. That's your outcome. And then you eliminate anybody who has ADL between 0 and 4 at the beginning of the follow-up. But you're going to end up with a lot of people with ADL between 0 and 10. Okay, well, you have a lot of possibility of contrast, but your best contrast is between 10 versus people who are no more than 4, no more than 3. It depends how many people you have. Let's say you end up with 1,000 people, less than 100 end up with ADL of 10. That's the worst ADL after 5 years. Say 100, 10%. Okay, then the other 90% distribute between 0 and 9, but more so around 4. There's about 30% around 4. Okay, and then about 20% below 4. So you have 60, about 60% below 4. And then you have those between 4 and 10. You could do a contrast analysis of relative risk or risk ratio between those who have reached 10 and those who have reached from 0 to 5 only, or 0 to 4 only, because that's the higher contrast you can get. So when you have higher contrast, you have more of an effect of what you're looking at, okay, for the outcome. You do the same with the physical inactivity in the active people. The best contrast to be very inactive, mean 0 exercise, versus those, depending on the age, who do some regular exercise at least 3-4 times a week, 4 times a week. How big is bigger contrast? Now, you need to reassure yourself that this analysis is done for all levels, but your large contrast is going to be between those at extreme. That's what we mean by contrast. You need to have adequate sample size, and therefore, if you do a contrast between ADL, the 10 versus those from 0 to 4 only in your cohort, and then you do highly active, very, very inactive, you may have very few people in these 4 subgroups. And therefore, you don't have power in your analysis. Your confidence interval includes the no hypothesis of no relationship, which you're going to see later on is the relative risk of 1, okay? Or incidence rate ratio 1, or risk odds ratio 1. Okay, if you have that, if the confidence interval include that, you got nothing there. So power is important. The idea of the prospective versus historical cohort, again, you can revisit that at some point. We're going to skip. We're going to go straight to how to calculate person time. We've done it before. I'm not going to show it to you. You skip it. Just a few words. The prospective cohort, disease-free, exposed, and unexposed are followed up. And the historic, yes, disease-free, exposed, and unexposed are followed up prior to the initiation of the study to measure incidence over time. So, you know, the difference between them is that one is subsequent. The other one is prior to initiation of the study. And retrospectively measure that. It's how I collect the data. It's not really how the dynamic of time is measured. We still have an underlying follow-up process. Here's a cohort, the nurse health interview survey or study, and not a survey, it's a study. And their interest here is silicone. That's my exposure group. Exposed to silicone. People have a transplant of their breast with silicone versus no silicone. And your interest is connective tissue disease. Are you familiar with connective tissue disease? Something like lupus erythematosus, collagenous disease, like, you know. Actually, arthritis, rheumatoid arthritis is one collagen type of, you know, disease. So it could be lupus or something like it. 2 ways for collecting data. Prospective cohort is a little bit better if you can, more reliable exposure data because you're actually measuring and starting after you measure exposure, you start following people up. Data available for potential confounding factors is usually more available. Longer completion time, more expensive. That's a limitation. The other one would be cheaper, faster, but, you know, shorter completion time, less expensive. But the exposure data, you have to rely on records. And maybe the records are not accurate. When you create your own records, you become more accurate. Data not usually available for potential confounding factor because you have to collect what is available. So you may not have an important confounding you're interested in. Say, oh my God, that's a retrospective cohort. So it suffers some of the same problems case control as far as data collection, exposure type of collection. Okay, but it's still a cohort and you're still following up and the actual incident cases of people happening over time. Like I said, well suited for studying rare disease cohorts, can study multiple effects of a single exposure because you can follow up any. I say my interest is ADL, but hey, people die in that period. I can also study physical activity in that. Oh, people develop heart disease. They didn't have it before they developed. I studied that too. So contrary to a case control I started already with the disease people and follow them up, right? So if my interest is ischemic heart disease, I only have ischemic heart disease. But here, I can follow up any disease, any outcome that happened in that time period among those in my cohort. The reverse is true also. Even though in a case control I'm limited to one disease, I'm not limited to the exposure. I can measure retrospectively any kind of exposure. Here, I'm limited to the exposure I initially start measuring, especially in the prospective cohort, that you measure the exposure in a subsequent follow people up. Okay? To measure association, rate and risk. Rate is the speed of occurrence and risk is the probability of occurrence. We went over this. We're trying to estimate the relative measure of effect, the effect of the exposure on the outcome. And these are risk ratio, rate ratio, and risk odds ratio. Incidence density cohort data is how I present the data. Can you see that? I don't know if the words are too small. They're getting very small, difficult for me to read. But it's okay on the slide. Do you think it's okay? Okay, so again, over and over and over, you have your person time calculated for each group cohort, exposed and unexposed. Okay. By the way, just look at a table like that. If I'm measuring the incidence rate of cancer in a city, what I'm looking at is M1 over PT. Is M1 over person time total for the whole city. But if I divided the city exposed to a water treatment plant contaminated with something and unexposed to water treatment contaminated with something, then A1 over PT1 and A2 over PT2 are the incidence rates among the exposed and unexposed. Okay? So you have those rates. I call them instance E, instance U, unexposed, exposed, exposed, and exposed, and total instance M1 over PT. But if I divide one instance, one group by the other instance, I have the instance rate ratio. If I take the difference between them, I have the attributable risk, which is the instance rate difference. We're going to have, hopefully, a little time tomorrow. I'm going to give you just 15 to 20 minutes. Burden of disease, measure of burden of disease. Start with this, with attributable risk difference, which is the attributable risk. Okay? Count data. It's the same cohort, but now I'm presenting differently. I'm presenting A, B, C, D. First is Terry Leeds' study on cabbage, thoracic surgery and infection on the surgical site. Obesity was my exposure. That group there is a short follow-up period, and I have a lot of people. I'm not too worried about person time. I'm not too worried about speed of occurrence. I'm worried about whether it occur or not. So I look at the risk ratio. So that's the data presentation. Is this one here. Okay? Is A, B, C, D, M1, M2, N1, N2. So I have N1 people exposed, M2 people unexposed. And over time, I measure M1 cases, new cases, of which some are exposed, that's the A, and B are unexposed. And vice versa for the non-case group. Okay? So what you end up to is two risks. Risk of exposed divided by the risk of unexposed, that's the risk ratio. And the risk difference is the risk difference. Here, it was the rate ratio and the rate difference. If I say risk, I messed up. So these are the data presentation for the cohort. Are we 1 hour already? Are we 1 hour, 40 minutes? How much we? When did we start it? Yeah, we need to take a break here because I'm going to let's do a shorter break at 10 minutes because I want to finish this measure of association, showing confidence of everything, what you learned in statistical foundation early on today. You're going to see why we're using this formula and not that one. Okay? So this is a cohort study. We finished. I skipped through a lot of stuff because you're doing the course much faster than you should. You know, in 3 hours, you should be giving no more than 2 lectures. I'm giving 3 lectures to all of you every morning. So we do it in about 10 minutes. We'll be back.
So that's good. Yeah. Sharing. And now let's look for your presentation. This one?
Yeah.
So, okay. Presentation mode. And let's do the upload. Is already sharing. That's it.
Okay, people. Can you see that on the screen, Ali? Can you see them? If it's showing there, it's showing to them. Is that right?
Yeah.
Okay. If you have any troubles, just send a message. There's somebody that's monitoring everything here. So welcome back. First off, I didn't realize you have not received the lecture we sent yesterday. Yesterday, I had sent a little bit late, unfortunately, because I had to work here until late with Dr. Ramos. But I sent the lecture, and somehow we went to, what was that, Fred? Went to my message with all the lectures from yesterday.
Yeah, because it was not, it came straight to my mailbox, but I have already received.
You went to where? Where did you go? I sent to your email, right?
Yeah.
Yeah, I sent to his email.
I will send now.
Yeah, I think their system, security system. Spam box, so it automatically redirect to spam box. I am sorry for that. You should have received it, but by now you should be receiving it. But it was sent yesterday like I had promised, but unfortunately, again, a little bit of a glitch. So let's go back to measure of association. Now you know a little bit how to do a case control in a cohort study, more important, a cohort study. Let me reframe this. It's very important you understand how a cohort is done, why we do a cohort. the fundamental statistic behind what I gave you today, Poisson binomial. And the variation of Poisson is called negative binomial. You need to remember that. I didn't show you, but it's very similar to the Poisson. Is because the intervention studies, that's the cream of the cream tomorrow. And after tomorrow is the synthesis, like meta-analysis. They are basically the best intervention studies are all, it's like a cohort. Actually, they are cohort. Every intervention study, clinical trials, is a cohort. The only difference between that and observation design is that in the intervention, you actually controlling the exposure. You scientist, you define the exposure, okay? Whereas in observational design, you are observing phenomena happening. People take up smoking because they're, didn't know better, turning of last century, over the past 60 years because they're stupid, okay? So that's different than you say, you do this, you do that. So you allocate people. That we're going to see it tomorrow. But you still have a cohort. You still have a longitudinal. You still have risk. You still have rate if you want to calculate. You still have risk duration if you want to calculate. Everything. And some other measures. Okay? So it's fundamental you understand the cohort. So we're back to the cohort design here. You have time 0 to time 1. Exposed cohort, non-exposed cohort. You're following them up over time. You can call prospective cohort because you start exactly in 1999, go all the way to 2003, or because you historically went back. A retrospective cohort can also be historical. You can go back in data and reconstruct the prospective time from 95 to 1999 and create another study. And you have the situation you can calculate these babies here, the person time for each group, the exposed and the unexposed group, and then tally how many develop the condition, how many don't, in each group, and divide that number of new cases that you tally divided by the total person time to get to incidence rate, or the total number of new cases divided by those at risk for becoming a case at the beginning and follow-up. That's a count data, and that's your risk. Here we go. Incidence rate ratio and incidence rate difference are the measures of associations. So how do we go about measures of association? What do we do with a measure of association? What we want here is go beyond measure of occurrence. I have occurrence in one group, and I have occurrence in another group, exposed and unexposed. When I contrast them, exposed divided by unexposed, I create a ratio. So I create an implied decision to interpret like this thing is causing this thing. The exposure is causing the outcome. And do I have a claim? Yes, I do. Because I know for certain the exposure precedes the outcome. So it's not a cross-sectional study. And I also studied, before I created the cohort, I studied a lot of possibilities. Maybe there was a case control done. Maybe there are 3 case controls showing these associations exist. Are they causal? Best way to do it is a cohort design because it doesn't sort from the biases of case control. The biggest bias of case control is selection bias. Okay? They control well confounding, but they have a problem with selection bias. And sometimes misclassification exposure is possible too. Whereas in a cohort, you do not usually have selection bias unless you have lots of loss to follow up. Okay? But if you are able to create a decent cohort, you have good records, and people are engaged, you find a way to get incentivized and get the people to participate and not drop off, you have an excellent cohort. You have a better chance to represent this association a causal way. Okay? So you end up with this thing. So what do we do with the rate ratio? What do we do? How do I know this rate ratio could have risen by chance? Okay? When I did the rate ratio, in that case I mentioned to you, the bronchiolitis obliterant association with exposure to fumes and the factor. It was not even diacetyl at that point. Only later I refined on diacetyl. Okay? So at that point, the rate ratio says 15 to 1. The rate ratio is 15, meaning those exposed are 15 times more likely than those unexposed. And exposed in that factory, I told people who are involved in the day-to-day operation of creating the sauce or the butter vat, a big vat, gigantic vat, the size of a mini room with lots of liquid, and they will have to mix. It's called the mixers. Okay, so I consider those people exposed to some major environmental contaminant, and the people who are in the office across the street on the same factory, but white collar office staff, I consider they unexposed. Guess what? the rate on one group was 15 times greater than the other group. So therefore, I got an incident rate ratio of 15 times, a relative risk of 14 point something. Okay? They don't always give exactly the same, but they should be similar. So the rate ratio and the risk ratio is very important. But how do I do? CDC asked me, could have a reason by chance. I say, first off, remember this. The greater the measure of association, the size of the measure of association, the magnitude, the more unlikely it is that's reason by chance. Something is operating there. In epidemiology, we use chance. We want to eliminate chance, but we don't believe in chance. We believe there is a systematic reason why people get sick. Okay? My brother, twin brother, was the same gene. We have the same digital, which is extremely rare. Could not have developed diabetes if he had not gained 50 kilograms for the past 25 to 30 years. There was no way. So there's a cause. We want to eliminate chance, so you want to make sure there's something that's beyond chance. So they asked me, how do chance play a role here? What do I do? Any guess? How do I take chance out in medical epidemiology, in public health statistics, or in statistics? I can do a statistical testing, right? What statistical testing could I use here? What statistic could I use? This is a density data. In this table, any disease, we're talking about, have incidence rate ratio. What is the fundamental statistic underlying incidence rate ratio? Remember, risk, binomial, incidence rate ratio, rate, Poisson, right? I could do a Poisson testing. Or I could create a confidence interval using the Poisson distribution, because I know what the variance is, right? So 2 times the variance, I can approximate normality if I have large numbers, standardized normal. I could not show that to you. You need to go back to basic statistics. See, how do I get standardized normal? Can a binomial, a Poisson, a hypergeometric become normalized? Yes, you can if you have large numbers. Law of large numbers. I didn't show you, but just remember that. Any one of those distributions can become a test statistic, a T test or a Z test. Okay? So you could use a Z or T test if it's large number. If it's small number, you use to have exact probability. Then we use the Poisson for the cohort or the binomial distribution. So I decided, okay, I have something. This is all in theory now, folks. So under the no hypothesis, H sub O means no hypothesis. The cell A plus B here, okay, is estimated by M1. Is my best estimate. Is the total. Okay, it's a random variable that follows a Poisson distribution. Actually, A follows a Poisson distribution, B follows a Poisson distribution, and M1 follows a Poisson distribution with parameters mu and variance mu. Okay, which in this case, the expression of the variance, the value X, probability of big X being X is M1. And M1 PT, which is M1 divided by total person time, that's the overall incidence in the table, follows a Poisson with parameters M1 over PT and variance M1 over PT. Okay, A is the realization of the random variable X, M1. And APT, A divided by PT, is the realization of the random variable Y, MIPT. So what I'm basically saying, folks, is this. The M1 here, let's say I'm looking to a little town of 300 people, okay? A little town, 300 people, and their 1 year follow-up time is 1 year. That's 1 year time, right? And assuming this population is stable and dynamic, even though it's small, it should not, it's dangerous, but let's say assume it's dynamic, I know that the total person time, PT here, is going to be 300 multiplied by 1. 1 year follow-up, 300 people in a small town, so person time is 300, okay? And I do have new cases in that city. There are 5 new cases in that city, 300 people. So 5 divided by 300 is M1 divided by PT. That's the incidence rate of whatever I'm interested in that city. And A over PT1 is an expression of that is a function of the exposure. Is the probability of being M1 given that I'm exposed. Is A over PT1. Okay? So I can construct confidence interval or statistical testing around that. So implicit in this hypothesis tested probability of finding a realization of the random variable X that is equal or greater than the observed A, or away from the mean M1, which is A plus B. Okay? So that's how you construct this. You construct a null hypothesis of the incidence rate, A over PT1, I assume follows the Poisson, and the expectation of that is M1P. It's my best expectation. It's the general incidence rate in the community. That's my parameter. That's my mu or my lambda. Okay? And the variance of that is also lambda. So IR follow then the Poisson distribution, and I measuring all of that directly with APTE, which is different than Y over APTB. Okay? So that already is an evidence. If A over PT1 is very different than M1 over PT1, is evidence that something's going on. I'm violating the null hypothesis. The null hypothesis basically say A over PT1 equal to M1 over PT. Okay? So alternative hypothesis, if the 95% confidence interval around APT1 does not include Y, or Y over, in this case, M1 over PT, then reject the null hypothesis HO and accept the alternative hypothesis HA. So how you do this probability? You use the straight Poisson distribution. Okay? You built this probability here, and you come up with this, E over -1, that very old thing you know. You studied this morning. And you can calculate also a lower confidence interval, upper confidence interval using direct estimation methods. It's a little complicated. But you can also say, I have no 300. I have like 500 people, 1,000 people in my cohort, or, it's big enough. I'm going to approximate to a normal distribution. Then you can use something like that. Okay? You can say that the test statistics say X, whatever value of A that I found, minus mu, and I know mu should have been M1, right? Square divided by square root of mu is going to follow a Z distribution, which is normalized standardized distribution. With parameter mu and mu. Okay? So the test statistic goes like that, and you can simplify that with the square root of 1/4 using delta methods and calculus, which I did not show to you. These are simplification of the methodology. So instead of using this formula, which is the exact measurement of the probability lower and upper bound, you can follow that. I use this much simpler. This little wriggling here is just square root, okay? So here we go. Got the formula. There's a little bit different presentation of the same formula. I can say square root of X follow a normal distribution faster than X itself, okay? Where X equal A. So variance of A is going to be this function square variance of delta method, which gives you that 1/4. That's the little bit of a derivation. So that is your formula for confidence interval. Basically saying square root of X, let's say A is 5 people with cancer out of 300 people, or 300 person time, total person time, okay? So once you got that, you do X is 5, so square root of 5 plus or minus 1 minus 96 square root of 1/4. See how it's a simplification? It's based on the delta method. But this is all the fact that it all coming from a Poisson, and a Poisson's large number become closer to a normalized distribution by law of large numbers. And the binomial also, when the numbers become big, become a Poisson, and the Poisson becomes a normalized distribution. You see that works? So that's your formula that I want you to use, the formula at the bottom here. Square root of X plus or minus 196 square root of 1/4. That's a quick and easy. Every time you have more than 300, more than 100, but ideally in the hundreds or thousands, you can use that approximation. It's going to give you a decent confidence interval. If the confidence interval do not include the null hypothesis, hey, you got something there, okay? So that's one way to test, doing hypothesis testing in confidence interval. That's the other way. I'm showing a second way. It's another formula, okay? If the confidence interval does not include 1, then you reject the null hypothesis. This formula is a little bit more elaborate. It's used the mu itself, multiplied by PTU, divide by that. So I'm giving step by step. Still using the other approximation, when the Poisson becomes a binomial with fixed margin, okay, you end up with this. And the Z for the normalization for that mechanism is this one here, okay, this formula. I don't want you to go hang up, just play with the formula. Throw numbers, create your own table like this. This is one exercise I'm going to ask. Create your little table like that, put real numbers in. You see how I'm presenting the table a little different? It's the same table, folks. It doesn't matter if it's a horizontal column. As long as you know where we're going, right? You have exposed people, you follow up, and you have disease happening in a follow-up time. Before I had reverse, I have transpose this matrix here. You'd be like exposure in a column and disease in a row, it doesn't matter. Okay, but place some numbers here and plug these formulas, see how it works. And send it to me, and I'll make the correction if you're curious about it. There's another formula for it, for the incidence rate ratio, which is based on the straight definition of the thing, but it's a little bit more complicated. You need to look at F statistics with the alpha over 2, which is 0.025 in each end of the F statistic, and 2 to the B plus 1, 2A. This is straight from the 2 by AB, PT1, PT1, PT2, and PT, okay? So that's another way to do it, and you can find in the table F statistic, and you can calculate the lower and upper confidence interval. So I'm giving you already 4 formulas for confidence intervals. And the other one, which is even easier, is based on incidence density being a Poisson normalized too. So you end up with this one here. And Z is this whole thing over here. You see? A, B, C. You got it? Okay, now you have the same formula expressed differently. Now, this is an important concept. This normalization, you see that log, I'm taking the log of the incidence rate ratio or the log of the relative risk, is because the distribution of the relative risks, the measure of association, or the incidence rate ratio, measure of association, is skewed. It's very skewed to the right. And when you take the log of this, because it's an exponential curve, if you take the log of an exponential, the exponential comes to normality, right? Okay, so you want to calculate the confidence interval around the log of the incidence rate ratio. And the variance of the log of the incidence rate ratio is that one over A, 1 over B, square root of that. That's your standard deviation. 196 multiplied by that's going to give the confidence interval to the left and to the right. That's a formula that's very much used, especially for count data presentations, like the case of the thorax surgery. I'm not interested in course of time, the short period of time. I'm interested in actual risk, relative risk or risk ratio or risk difference. I use this formula. It's again, it's the Poisson is going to become normalized after hundreds of cases, or better, hundreds of people in your experiment, in your cohort, especially if you have 1,000 people. Real number example here, I'm giving to you a cohort study with 5,912 person time observation for the exposed group and 3,408 for the unexposed group. There are 18 cases in the exposed and 25 cases in the unexposed. So you end up with the incidence rate ratio as you see it here, which is 0.4. That means whatever is the exposure here, it protects you. It prevents you from getting disease. It doesn't cause disease. It's the unexposed group that have the most or whatever. So having the exposure, it could have been, let me see, it was hypochlorite. Yeah, absolutely, I should have read. This is CDIF, that's infection in the surgical site, and use a hypochlorite to the soil. Okay? So that's a disinfectant, very cheap and easy, and they prove it beyond doubt here. If you use that, you're not going to cause infection, you're going to protect infection. So your incidence rate ratio is protective, and the confidence interval using one of those formulas there. Which formula did I use for that? Oh, I didn't show the formula. I think I know I used this one here. I used that formula here for that calculation with the F table. Okay, F statistics. By the way, folks, table of statistical probabilities is going to show you to use Z, X, which is chi, which is basically chi-square, remember? And F. F is a function of the chi and vice versa. They're all functions of each other. Remember, F of F, Functions of functions, that's what we're dealing with here, okay? So cohort study risk presentation, a little different. Even though this last formula was a risk formula, I gave it to you. It was drawn in the wrong way here. Should be in the other place, should be on the other side. But it's used too for its district ratio, but it doesn't give you the best solution, promise you. It's good for risk ratio. Cohort study presentation, it's a binomial here. We're gonna use binomial. Remember, it's very simple. Binomial is a proportion. So if I have 10% of the population with diabetes, and then I have 90% of the population do not have diabetes. So my variance for that is going to be P, it's 0.10 multiplied by 0.9, 0.9, okay? And that's 0.09 divided by N. Let's say my sample of the 100 is 0.09 divided by 100 is 0.009. You with me? That's your variance. Take a square root of that. I don't know. It's going to be 0.003, right? And then I multiply that for 196, about 2. It's 0.006. I found a risk ratio of 1.5. It's going to be a 1.5 plus or minus 0.6. It's going to be a 0.9 to 2.1. You did in your own head. So include the confidence interval of the risk ratio being equal 1, which is no effect, no association. So I can't prove I did anything wrong. So binomial is much simpler. Okay, so here we go. But I gave a different formula, which is more complicated, but it's good. Actually, it is the same formula. What am I saying? I saw a bunch of M's, I got confused, but actually it's PQ over N there. If you look at the table, how I use the labels P and Q. So it's a Bernoulli type of thing, situation. You end up with this, you end up with PQ over N. Okay? This is the direct probability, mean direct, exact estimation of the probability, use the binomial formula. But I want you to be more acquainted with using a normalized distribution. It's a little different here, okay? And there are many formulas. One of them, the one I gave a little bit before, 1 over A, 1 over B, but it's also for rate. That can be used here too. But the other one is this one, Z equals A minus N1, M1. M1 multiplies M1, divide by T, that's a total. And this is a count data table. It's not density. There's no PT percentile. It's, N1 people exposed, N1 people unexposed, M1 cases, M2 non-cases. Okay? So you end up with this formulation here. And it's all based on the binomial. And just take the square root of that. So N1 divided by M1 over T, that's nothing more than N multiplied by P. Okay? So the big N, the big M multiplied by T, the big T is going to give you the value of A, the expected value of A. Then you divide that by the variance of that, which is PQ over N. N1 to multiply M1 over T, okay, M2 over T. It's PQ over N multiplied by N. It's going to give you the variance. Okay, it's going to be Z of normal and the variance of that. So here's the formula for the 95% confidence interval. I think I'm going to give a real number. If I'm not crazy, I didn't know. I'm going to show another confidence interval. Then I'll use some real number. That's another way to calculate. Is this one I want you to remember. That's the normalized way of calculating a risk ratio confidence interval that does not require any understanding of the exact probabilities and even remember the formula binomial. Just remember, it's a little formula anyway, but 1 minus A, which is basically saying, hey, it's not just A. Remember, it's A over A. So it's 1 over something. So 1 minus A, then multiply, then divide A plus B. So it's 1 minus A divided by A plus B. It's the other side of the proportion. 1 minus the proportion is going to give you the other side. All this quantity divided by A plus 1 minus C over C plus D divided by C. Okay? And then you exponentiate this whole thing, 196 minus plus or minus is going to get you the confidence interval you need. Example here. That's Terry Leach's study on cabbage surgery. Remember that? Open heart surgery. So you got remember that I told you they don't care about person time because such a short period of time, I care about the risk here. Okay. So you have a cumulative instance or risk. Okay. And then you have your 1 infection over 100 cabbage surgeries. Relative risk. This is your formula. It gives you a risk ratio of 2. Where's the confidence? God, I forgot the confidence. If you plug the numbers, do that homework yourself. I thought I had done it. Plug those numbers in the formula. You plan that in Excel. If you show me an Excel formula, I'll give you 100, your best grade possible. Create a formula in Excel based on this formula here. Sorry, this formula here. Okay, 1 minus A divided by A plus B over A, whole quantity over A. 1 minus C over C plus D divided by C. Square root of that, multiply by 196. Okay, and then you exponentiate this whole quantity, and relative risk is going to give you, multiply by that, it's going to give you the confidence interval. Okay. So I think I wanted to finish before time. The most important piece here is that you need to always relate your test statistic, your confidence interval for measure of association, and the measure of association itself with the original distribution, where these things are coming from. So you understand why we're doing those things. Okay. I want you to ask me questions so I can answer. Tomorrow, we really start a new, but it's still thinking about the framework of your horizontal way of looking at a cohort study in an intervention trial, randomized clinical trial, pragmatic trial, natural experiment. I'm still looking into prospectively. And I'm looking at person time. I'm looking at total risk. I'm looking at total N. All those same thing as an observation design, except that you now control the exposure. That's the only difference. And you randomize people into groups when you do a randomized clinical trial or randomized intervention trial. No questions. Okay? We're going to see that. But ask the question later. Send me message. I'll have a little bit more time free today. Yesterday was pretty busy after here. And I only send the message with all your lectures to Fred late at night at 8 o'clock my time. I forgot it was 10 o'clock here, time here. I was working. And it was in his dirty box, whatever you call it.
Spam box.
Spam box. Okay, so, but today is not going to happen. No. As soon as I get to the hotel, in about 2 o'clock, I'll send it to all of you. Or we did today. You can review this exceptionally rich material that I covered too fast because I want you to read. I want you to try to do some of the exercise. Take some of the examples I gave, create new ones, read some of the paper, replicate their tables, calculate those things. Okay? Thank you. I'll see you tomorrow with the intervention trials. And then the day after tomorrow is about meta-analysis and systematic reviews.
Great.
Okay? Thank you. Bye.